Okay. So if you look at your Putra Blast, so for this week, last week, so we had a tutorial, second tutorial, right? We did together during the class, I think so, the both two exercise. So the deadline for submission is tomorrow, 36 October, I think I set at 1 p.m. So now there are already 16 students submitted. So 9 more, okay? Okay, so that is for tutorial last week's tutorial from actually I typo a bit the title for the slide, but the question I think are correct. The exercise, tengok. Kejap. Mana tadi? Sorry. Mana tadi? The exercise, okay, the exercise were correct from chapter 2, but the title I didn't edited it, okay. It should be tutorial 2. Okay, so this one was tutorial 2. So deadline for submission is due for tomorrow at 1 p.m. Okay, so 9 more students, 21 hours remaining, okay. And then okay, so this one I've just uploaded, okay, MCQ2. I've just enable it since 12 p.m. just now. So you have, since we are doing online this week, so I give like more or less 24 hours, more than 24 hours for you to do this MCQ of last week's chapter, exercise 2, the pure substance, okay. So as previously chapter 1, MCQ 1, so you need to answer 10 questions, A, B, C, D, etc. So but I give you until tomorrow 5 p.m. But if you have time after our class, you can do it directly. But I open it until 5 p.m. tomorrow, okay? So don't forget to do this, okay? I'm afraid that you forgot to do this, okay? So just go to the Putra Blast. It's on topic number 2, not this week's topic. It's in topic number 2, which is last week's chapter 2, the pure substance, working fluid, ideal gas, etc. Thermodynamic tables. So MCQ 2 is here. So don't forget to answer this. Okay, and then now, so today, this week, I'm going to introduce to you the chapter 3 actually. Okay. Before that, if you see the video online course Google Meet, like week 2, this one, right? This was like last year's or last 2 years during PKP, I did the recording. So so the chapters the chapter and the weeks might misplaced a bit, okay? Maybe I week 2, but I did chapter 3, etc., because the syllabus was a bit different, but the content plus minus is the same, are the same. If you need to look back the content of the course, you can just look at the video that I've recorded like last year or 2 years ago. Okay, so for this week, we're going to start chapter 3, first law of thermodynamics. I'm going to introduce you the first law, and we have this tutorial. Okay, tutorial number 3, which is the due date is next week, Thursday next week, 2nd November. Okay, so don't forget this one. You have okay, first you have this one, tutorial 2, which is tomorrow, 36 October, but we have already started last week, so should be you have already finished, except 9 of you. And then we have MCQ 2, I've just uploaded, I just enable it. So this is for tomorrow also, but just MCQ questions, 10 questions for chapter 2 last week. Okay, so for this week, okay, we're going to start chapter 3, and we have tutorial to do, which is the due date is next week, Thursday, 2nd of November. So we will see each other first before the deadline, in case you have any questions. Okay, so now let's start chapter 3. Okay, there are already 22 of you. All of you are from my group, right? None of you from Dr. Izani's group. Are there any of you from Dr. Izani's group? Ada ke daripada Dr. Izani punya group? Because I did share the Google Meet link to Dr. Izani because she said that maybe his group can join because I think they don't have class this afternoon. But it's okay, just want to make sure. Okay.
I am from Dr. Izani's group, doctor.
Oh, okay, you. Sorry, what's your name?
Hatem.
Hatim, okay. So one oleh Hatim okay. Okay. But it's okay. But because I just think that Dr. Izani and me we kind of like switch chapter 2 and chapter 3 because my class last week we have done chapter 2 regarding pure substance. Okay, so this week we'll do the first law of thermodynamics. I think Dr. Izani he did the chapter 3 first and then this week should be chapter 2. Anyway, so if you already here, just join us and listen to us. Listen to me, okay? So so chapter 3. Okay, so the slide is in the Putra Blast. You can download, or if not, you just look at my slide here. I think you can see my slide, right? Okay, first law of thermodynamics, chapter 3. Okay, some introduction. Again, we revise back the definition. Okay, so heat, first heat, the form of energy that can be form of energy that can be transferred from one system to another system. So anything, energy that we, especially regarding temperature, right? The temperature, once we have a temperature difference between two body, means two medium, okay, liquid, gas, or solid, etc. When we have a difference of temperature between a two medium or two body, we call, or two control volume, then the heat from the hotter body, I mean the higher temperature body, the higher temperature medium can be transferred to the lower temperature medium or body. Okay, I think you understand that. So naturally the nature, okay, is always like that. Even though without any electrical appliances, power, etc., if we have a two body or two medium, one with a higher temperature, so it will slowly during a certain period, after a certain period, the higher body, the higher temperature body will transfer slowly. It hits its temperature to another medium which is with lower temperature. So that transformation, that transformation of energy, it's what we call as heat, heat transfer. Okay, so we have also thermodynamics, is the amount of heat transfer again. Okay, so thermodynamics we relate a lot with temperature, dynamics, pressure, velocity, etc. So if we state, okay, just now heat, okay, just the meaning of heat. Okay, now heat transfer, what we means by theoretically means heat transfer. Heat transfer is the rates of energy. Okay, when we mention rates here, means something that something that we measure, of course, but in terms of per seconds, usually per period of time. Rates is something that per period of time. So usually when heat transfer, we use the unit watt, hour, watt, W-A-T-T, watt. So watt is actually joule per second. So joule is the unit for energy. So energy per second, the rate of energy. So the rate of energy is actually power. Okay, because power, watt is joule per second, joule is energy. So energy per second per period of time is rate of energy. Okay, so it is watt power. Okay, same thing as mass flow rate. So the rate of mass flowing through a certain volume, etc., through a certain medium. Okay, so heat transfer is actually we want to determine the rates of such energy transformation. Okay, the energy transformation just now when we have two body, so the rate of that transformation of the energy is what we determine as heat transfer. Okay, so the transfer of energy as heat is always from the high temperature to the lower temperature one, of course. heat transfer stops when the two mediums reach the same temperature. So when the two medium or two body or two volume, two fluid reach plus minus reach the same temperature, so we call them as thermal equilibrium, means both of the body, both of the medium are in thermal equilibrium. Okay, I already introduced you that term, I think in chapter 1. So both of the medium is set as are in thermal equilibrium when both of them reach plus minus the same temperature. Okay, so in reality, even though it states here its heat transfer stops when the two mediums reach the same temperature, but you don't really expect it to be exactly the same temperature. Usually not 100 and 100, or it can be like 100 and 99.5 degree or 98 point, even 98 point degree means 2 degree difference. That's I mean that's small, very small difference also can be accepted as that the both of the medium are in equilibrium. Okay, so in reality is maybe it's not really the same exact amount, but nearly the same, so it can be assumed as in thermal equilibrium. Normally we need to assume, we need to make assumption that the body, the volume, the fluid are in thermal equilibrium. Otherwise, we cannot apply all the equation, the law that we are going to learn. For example, the most important one, first law of thermodynamics. In order to apply the first law, the ideal case of the first law of thermodynamics, first we need to assume that the case study, the volume that we are studying, are in thermal equilibrium. Otherwise, we can apply the law. Okay, so heat can be transferred in 3 different modes. Okay, have you ever heard about conduction, convection, and radiation? Okay, so conduction is between, first I'm asking, okay, so conduction is between, how to say, which types of fluid, atau which states of fluid, solid, or liquid, or gas, and what is, at least we need two medium, okay, two body. So conduction usually is between liquid and liquid, or liquid and gas, or what? Nur Aini Amirah, are you there? Nur Aini Amirah, dengar ke? Can you hear me? Kalau tak boleh dengar, boleh, if you cannot hear me, you can type. Saya mute ke tak kan? Are you there, Nur Aini Amirah? Otherwise, I assume you are absent. Okay, anyway, I go with Nur Muhammad.
Can you hear me?
Yes. Okay, so Nur Muhammad, conduction is really heat transfer between which body, which state of body and apa dengan apa? Solid dengan solid ke, solid dengan liquid ke?
In my opinion, solid and solid.
Conduction
Conduction.
Okay, thank you. So conduction, usually solid and solid. So like simple conduction through building, right? To surface, okay? So two materials, we have a conduction types of conduction mode of heat transfer. Okay, there are 3 modes. Okay, the second one is convection. I ask Molly, Irma, Ana, apa ni, tak nampak apa ni. Okay.
Yeah, doctor.
Yes. Okay, so convection is between what? Liquid solid, solid gas. Between those 3 only.
Within fluid.
Okay, fluid. Specifically?
Gas and liquid.
Okay, thank you. Yeah, correct. Okay, so usually we just call it fluid. Okay, so fluid means can be liquid or gas. So between liquid and gas and both 2 different gas also can. Okay, convection. Okay, and then radiation.
Doctor,
Yes, ini
Dr.
hi.
Sorry, I was in the toilet tadi.
Okay. So I was asking what is
Huh?
the apa tu the types of substance of in occur during heat transfer radiation mode. Okay, you try to answer for radiation mode. Is it between liquid and liquid, liquid and gas, or liquid and solid? Radiation
Gas.
dengan
Gas liquid.
gas dengan liquid. Okay, fluid lah juga kan.
Ah,
Okay. Can be, okay, can be, yeah. Okay, solid also can be, okay, solid and another type of fluid. Okay, asalkan as long as one of them is fluid, is a fluid. Okay, thank you Aini.
okay, thank you, Doctor.
Okay, so basically radiation, okay, in us, mechanical usually we involve with conduction, convection, and radiation. Radiation involves with as long as we have like an electromagnetic wave or a source of heat, like a source of like solar, like from solar. So the heat from the solar can radiate the surrounding, the temperature, for example. Okay, so radiation, as long as we have like like a wave medium, okay, like sound medium, okay. So normally for us in thermodynamics or fluid, okay, we involve with mainly convection and radiation a bit. Okay, but mostly regarding convection, thermal convection, heat convection.
Doctor, can I ask?
Hmm?
Does sunlight include in radiation?
Radiation can be convection pun can be juga.
Oh,
Okay, once the radiation is the emission or transmission of energy as long as we have form of wave kan. So the apa tu the energy from the solar tu, the transfer through the like ambient tu ada space, speed of light, okay, speed of sound.
okay. Thank you,
So
Doctor.
so when you have like solar and solar energy, there are two types of heat transfer mode: convection and radiation. So when we involve with solar energy or anything that have lights, we need to take into account these two modes of heat transfer. Okay, we can, but sometimes to simplify our calculation, our assumption, etc., we sometimes neglect the radiation part because it quite small compared to convection mode heat transfer. But if you do a real research, real experiment, normally we cannot neglect the radiation heat transfer lah. Okay, so for example, if we have fire, explosion, etc., so we need to take into account also the radiation heat transfer mode, not only convection. Okay, so all modes of heat transfer require the existence of a temperature difference. So once we have temperature difference, as low as even 2 degree or 1 degree, then heat will be transferred from one medium to one medium. Okay. Okay, so this example, okay, we look at this one first. Okay, heat flows in the direction of decreasing temperature. Okay, so the simple case study. Okay, we have a cup, a mug of hot coffee. So the hot coffee without any additional power or electrical power, etc. So if we just put the mug, the cup of coffee on table in a room temperature, for example, so after a certain period of time, the hot coffee will cool down. Okay, so that means that the heat from the hot coffee will be transferred to the surrounding environment. Okay. And then, okay, if for a thermos bottle, okay, what so we want to conserve, if we want to conserve the heat within the hot water coffee, okay, usually we use a thermos bottle which is act as a thermal insulation to insulate the bottle so that we can conserve the heat. But after a while, usually maybe after like more than 6 hours or 10 hours, the coffee will cool down also, but it take a longer time for the coffee to cool down, right? To decrease the temperature. Okay, so in order to conserve, usually we use a thermal insulation. Okay, same like in our building. Maybe in Malaysia we don't usually have that, but in Western country usually, because since they have winter season, so normally their houses or the office building, they will include add on a certain thermal insulator material to conserve the heat, so that the cool weather will not penetrate directly in the building. Okay. Okay, so application of heat transfer. Okay, so I already mentioned during the first week why we need to learn this heat transfer even though we are in aerospace program. So of course, because energy production, okay, mainly due to the energy production, energy conversion. So energy production can be in power plant, okay, to produce electricity, mechanical power, etc. But also for to propel the aircraft engine, we need, of course, energy, power. So the main cycle, thermodynamic cycle of the engine in the aircraft is based on the gas turbine cycle. So that gas turbine part we will learn later on after we learn first law, second law, etc. But this is the fundamental part before we learn about the gas turbine cycle. Okay, so or if you have renewable energy or other sort of heat source energy, heat source, solar, wind, ocean, all the transformation from the solar to power, to mechanical power, electrical power, from the wind, from the ocean wave, etc. So biomass, okay, those types of heat source energy, after the conversion, also apply the heat transfer process, okay, the heat transfer from one part to one part. The refrigeration and air conditioning, aircon, our refrigerator also needs energy, domestic applications for heater, shower, okay, cooling of electronic equipment, okay, manufacturing process, automobiles, etc. Nature. So just the same thing also. Okay, so like I mentioned just now, between as long as two body or two medium are in contact with each other, okay, the cold body can be the environment, okay, so the heat from the hot body will be transferred to the cold body, okay, so technically the molecules within the hot body will move, okay, will be in motion. It does possess kinetic energy. Then the heat from the hot body will be transferred to the cold one. Okay. So this just mentioned about joule. Okay, joule is the SI units, means the main units that we use to measure the amount of energy. Okay, so joule. Okay, moving boundary work. Nak ingat. Okay, moving boundary work. Okay, so work is one form of energy. So work, the unit for work is joule also. Okay, work, we write it as W. So W here is not watt, it's work. Okay, so work is one type of energy, the same as Q. Q is heat transfer. So Q and W are both energy. Okay, work and heat transfer energy. Okay, joule, unit joule. Okay, so so moving boundary work, working system, gas confined to a cylinder fitted with movable piston in thermal contact with the heat reservoir to exchange heat Q. Okay, so normally we will give example in piston. Boleh bayang piston. Okay, so we have like a certain volume of gas or liquid, usually fluid, within the piston. So within the cylinder. Okay, so we try to move the piston, whether we compress it or we expand the gas, okay? Whether we lower the piston or increase, okay, the piston. So we the work or heat transfer will be involved during that process. Okay, if we increase or if we lower the piston. Okay, so initial state of the system. Okay, for example, we have a certain pressure, certain V volume, not velocity, volume and temperature. Change to final state of the system, PF, VF, TF. Okay, from initial to final states. Okay, through absorption, positive Q, or release, negative Q. Okay, so normally work and heat transfer, it's in okay, no, sorry. Okay, through absorption, positive Q, or release, negative Q. Okay, so if you want to using a piston, example a piston here, if you want to positive Q means we produce heat, okay, or negative or release heat, negative Q, okay, means that we reject some heat, okay, by the system gas. Okay, so usually positive Q is the heat input when we absorb the heat from the heat source, or release, reject the heat, negative Q. Okay, so it means that during our calculation, for example, if we have the answers positive or negative, that reflects whether the heat is being absorbed or being released. Okay, so the direction, okay, the direction positive, negative of Q or W has meaning. Okay, by the system gas. Also, work W can be done in raising the piston. So if you want to produce work within the piston, using the piston, okay, so we need to raise the piston, okay, raise the piston. Okay, so we will have a positive W. Expand means that if you raise the piston, if you raise the piston, you can imagine, means that the fluid or the gas within the cylinder, the volume of the gas will expand, right? So the expand, I mean the increasing, the increment, okay, of the volume will reflect in terms of expansion, means that the gas, the fluid within the cylinder is expanded. So expansion is a positive work done, positive W. Or if we lower the piston, means like we compress the fluid, the gas within the cylinder. If we lower, then usually there will be negative W, because we will use up the work. In order to compress, we need work. Okay, so we use up the work. So the work it will be in direction negative W. Okay, so usually this part in a gas turbine or thermodynamic cycle, the positive Q here is really during expansion in the turbine. Okay, negative Q is during rejection. Turbine. Sorry. Positive Q is heat absorbed within the evaporator, the heat source. Heat exchanger, heat source, evaporator, boiler, combustion chamber, etc. If you remember, or I think you don't remember. Okay, but last few chapters, there's a okay lah, saya buka lah. Chapter, I think chapter 2 or chapter 1. Wait. Just to flashback the cycle. Last week ada ke sekejap okay. Oh, in chapter 1 Oh, ya. Sekejap. Because I want to link the piston with the gas turbine. So you see what I mean? Oh, tak ada. Oh, I think I didn't introduce to you guys yet, but Don't worry. I'll just use a picture that I have. But I will introduce this to you in next few chapters. Sini. Please ada. Ni. Oh ni. Okay. This one is actually in next few chapters, but I just want to link with what I'm explaining regarding the piston just now, so that you can see the link of that piston case study with what we are going to learn in gas turbine. Okay, so normally this is the main 4 components in gas turbine. Okay, 4 main components of gas turbine. Okay, so this is a closed cycle. Okay, not gas turbine for aircraft, but gas turbine for power plant. Okay, steam power plant usually. Okay, so you see Q in here. So Q in here is the positive Q. Okay, absorption of the heat just now. If you relate with the piston, okay, positive Q. So from the heat source usually, okay, positive Q, and then positive W. I mentioned just now is when we raise the piston, we expand the fluid, the gas within the cylinder. So that is usually occur in a turbine when we expand, okay, the fluid. So we produce power, positive W, work output. And then Q out is when we release the heat. So release the heat just now, it's negative Q, okay, because we reject the heat. So that one occur usually in a condenser. Okay, and then last one is negative W, work, is usually occur when we compress, right? When we lower the piston, the fluid within the cylinder will be compressed. So that usually in a turbine will occur in pump, compressor, right? We compress the fluid. So that one during within those device, pump, compressor, etc. The work will be negative. Okay, means that use up the work to compress the fluid within the cylinder, within the gas turbine. So we are using up the work. So that's why the work is negative. Okay, I just want to, we will learn this. Don't worry, we will learn this gas turbine cycle in next few chapters. But it's because I just want to relate with what we are learning today. Okay, so piston, because piston usually is what we call as reciprocating. Okay, because it repeats, reciprocating engine. Okay, gas turbine is not reciprocating engine. Okay, but the cycle, the thermodynamic cycle, heat transfer, work produced, work input, etc. I mean the theoretical cycle are the same. Okay, for engine. So for this type of engine, which is piston engine, reciprocating engine, okay, the work output, okay, because any engine, why we need engine is because we need to produce power. Simple, okay. We produce the engine because we need power. So the idea usually, if we produce the engine, we want to measure how much the energy can be produced from that engine. So the energy produced from the engine is measured using the work. Okay, how much the work are able to be produced from that engine. So for this type of engine, which is piston engine or reciprocating engine, the work is counted, is measured like this. Okay, so this is the equation. So work, what we call as boundary work. Okay, so boundary work because the boundary of the cylinder, the boundary of the piston. Okay, so so the boundary work W is the integral of P dV. P is pressure, V is volume. Okay, why P and V? You can imagine because in the piston, the main force, okay, because force also relate with pressure and then energy. The main force is due to the pressure, okay? Pressure and the area depends on the surface area of the piston and of the volume of the cylinder. So that's why the main work output to be measured, okay, we need to calculate pressure and volume. So integral, multiply. Boundary work. For gas turbine, the formula are different, okay? So here, just to explain a bit, the different types of process, okay? If you remember, we have process, path, etc. So the process from I, the initial point, to F, or from 1 to 2, the process, the initial point from I to F, the initial point of I and F can be the same, but the path taken from I to F during the process can be different. Okay, so understand the difference between process and path taken. Okay, process is usually means that the initial point and the final point, the initial and the final state, I and F, or 1 to 2, etc. But the path can be different. So due to the difference of the path, okay, different route taken, different path taken, so the work output are different. It's different. Okay, so mean that if we change the method, the path taken, we change the method of the process, even though the initial and final state are the same, but the method of the process are different, so the work being produced is also different. This can be visualized using graphic like this, okay? Since the formula, the equation is integral, so we know integral is usually the area, the total area within the range I to F, okay? So if you do graphic like this, A, B, C, we can see that the total surface area under the curve, okay, if you do the integral, are different, right? A, B, and C. So that's why the work produced, if we use different path, okay, from process I to F, different, so the work produced is going to be different, okay? So W work just now, okay, just to derive, just to explain how we derive the WPDV just now. So work is force multiplied with the displacement, force and displacement. In mechanical, force times with displacement, we have work. So force is pressure and area, force, pressure, area, okay? So if we just rearrange the equation, pressure, ADS, area, and the displacement, so we have volume. Okay, so that's how we derive the boundary work, W equals to PdV. Okay, so work done by the area under the curve on PV diagram. So if we sketch the process within PV diagram, we can see the curve like this. Okay, so so if the process contains a fluid, example gas, so we can assume that the gas is ideal gas. So we can, in order to calculate, okay, to evaluate the work, to calculate the work done, we can use the ideal gas equation of state that we learned last week, which is PV RT, PV nRT, PV mRT, okay, or PV RT. Okay, this is the ideal gas equation of state. So we apply the ideal gas to calculate W, means that P here is being replaced with RT over V, or nRT over V, mRT over V, okay? Because we assume that the fluid within the cylinder, piston just now, is ideal gas. For B, from I to A, process volume is increased at constant pressure. Okay, this one, for example, if from I to a certain point A, we the process is isobar, constant pressure, and then A to F is isocore. Isocore is constant volume. Okay, so means that to calculate the work produced from this process B, okay, means we need to separate it. One part during I to A and another part A to F. Okay, you know how integral, okay. So and then this one this one also, okay, so this one we start with a constant volume and then finish it with a constant pressure, so the work also will be different. Okay, so you can see the difference when you calculate the amount each of the process. Okay, so moving boundary work again. Okay, so depends on the area of the area, this one, area area. Okay, so you know the force is whether upward or downward. So the area is the normal, the surface area that will be counted is the normal direction of the force. Okay, so that's why area is the area of the piston here. Okay. So okay. So again, work boundary work positive mean expansion, like you are producing the power, or you're using up the power to compress. So W boundary work will be negative, the same as in gas turbine. Just that we don't have this D boundary work. We just call it work. Okay, so again, the different path follow, so different work produced. It can be seen when we sketch the process in a PV diagram. We see the difference, A, B, C taken. Okay, polytropic, okay, just take note of this one, but we seldom use it. Polytropic of gas, okay, just the difference between this one polytropic and the ideal gas, okay, means that we have a certain value that we call N. N is just a constant, value constant. So for a certain fluid, certain process, it has a certain amount of N, okay, and to characterize whether the process is isothermal or not. Okay, but usually we will just use N equals to 1 for isothermal process. So we don't see that N appear in our equation. Okay, we just use PV RT. Okay. Just I have a questions. What is the boundary work for a constant volume process? The boundary work just now, this equation, PDV. What is the boundary work for a constant volume process? What if you have constant volume? Means that the volume within the gas doesn't change throughout the process from initial to final state. So what happened to the boundary work? What is the amount of the boundary work? May I ask? Apa lagi? Ashwin?
Yes, ma'am. Zero.
Why?
Because no expansion, no anything.
Okay, so no, the volume doesn't change, okay?
Yeah.
Okay, so, okay, thank you, Ashwin. Okay, so if we look at the mathematically, the equation means that D is the difference in the small difference, okay, derivation. Means the dV is 0, so obviously the boundary work is 0, so no work done. Okay. Okay, next. I think this is just sum up. Okay, work provides a link between force and energy. Okay, so again, FDS just now, force times displacement. Okay, work. So starting from this definition, force times displacement, that we derive the boundary work equation just now, PDV, right? Okay. And then, okay, mechanic, and this is for more to solid solid mechanic. Okay. Also we can measure the work, okay, in solid mechanics. Work, so the displacement, if there's the displacement occur within x-axis horizontally, So the displacement will be F cos theta. Okay, the angle between the force applied and the movement, the magnitude of the movement of the body. Okay. So this is for solid mechanics. So we usually we will for aerothermal we will apply fluid mechanic. So that's why you are learning with fluid mechanic also this semester, not solid mechanics. So fluid mechanics. So the definition of our definition of work is different, but it's still derived from this definition, force and displacement. The equation is different, but it is being derived from this definition. Okay, force displacement. So we have PDV. Okay, so work, this give no information. So work cannot give information about time or velocity, the acceleration of the object. So work is a scalar quantity. Okay, yeah. So we don't know about the time taken during the expansion or the compression, etc. And we don't know about the velocity of the piston, etc. We cannot measure that using work. Okay, so units of work, SI units, Newton times meter, the force and displacement just now, so it becomes joule, or sometimes we write as Nm, or kilogram meter square per second square. Okay, so this one, like just now, the work done by a force is zero when the force is perpendicular to the decimal. So if we like, if the work is what to say? I think I have the like this one. Okay, when work is zero, the displacement is horizontal. Means that the what do you call this? So this cylinder is cannot move. Okay, if the force is vertical, but the displacement that we want is horizontal. So the angle of the force and the displacement is in 90 degree or opposite direction. So we cannot produce work with this. Okay. Positive with the force and displacement are in the same direction. Negative with the force and displacement are in the opposite direction. Okay. So due to the angle, work can be positive, negative. Okay. Okay, work also can be done by friction, okay, due to the friction. But usually work done due to the friction is work loss, energy loss, okay. So the energy loss to friction by an object goes into heating. So the energy, the work loss by due to the friction will be dissipated through heating, okay, both the object and its environment, okay. Some energy may be converted into sound, or some means that like I mentioned, not 100% the energy that we put as input will be produced as output, okay, not 100%. So the lack of the efficiency or the loss of the energy usually will be converted, will be transformed to friction due to heat, through sound, etc. Okay, so we might lose some sort of energy during the process from one form to another form, okay, which is in real case. Okay, then we have power. Okay, so power actually relates with work just now, work or heat transfer Q. Okay, so power is the energy or work here divide by time, period of time. So means that when we want to measure power, it's actually we want to measure the rate of energy transfer, because work and heat is energy transfer, energy. So how much is the rate of that energy can be transferred during a certain period of time, then that is what we call as power. Okay, joule per second or kilogram per meter square per second, per second. Or what? We can use what? We can use joule directly. So this is US, no, we don't use US units. Okay, kinetic energy, example. Kinetic energy is due to the motion of the object or the motion of the molecule within the fluid usually. Okay, so kinetic energy is written as 1/2 mv square. V is the velocity. V velocity here, not volume. V is the velocity, the speed. So it depends on speed and the mass of the body, the material. the substance. Okay, so it is a scalar quantity and it is a form of work, a form of energy. Okay, remember work energy, work is one type of energy. Okay, work is related to kinetic energy here. Okay, tak apa. Okay, potential energy, PE. Okay, so usually potential energy is due to the difference of altitude from a higher point to a lower point. Or it can also be due to the potential energy elasticity, spring, or apa tu, rubber band, okay, getah. So the elasticity, the energy stored within the spring, the rubber band is what we call as potential energy, and then that potential energy will be released after when we stretch the spring. Okay, also we have gravitational acceleration usually. Okay, so that gravitational force is one type of potential energy as well due to the altitude. Okay, so PE usually mgh, the mass, the gravitational force, gravitational acceleration, and the altitude, the height. Okay, conservation of energy. So from that transformation of energy from one form to another form, okay, remember energy cannot be created nor destroyed. Okay, energy cannot be created nor destroyed. So energy can only be transformed from one point to another point, means that the energy is conserved. Okay, so from this theory or this definition, this is how we derive the first law of thermodynamics. Okay, once that we know that the energy is conserved, cannot be created, cannot be destroyed, means we just can change the energy from one form to another form, from kinetic to potential, from work to heat, etc. Okay, all those types of energy. So energy is conserved. So from that definition theory, that's how we derive the first law of thermodynamics. So the first law of thermodynamics define and depicts that the energy is being conserved. Okay, sama lah. Okay, so simple example of conservation of energy. So E energy, so energy initial to the total of energy at the initial point, initial of the process, to the total of the energy at final point. So for example, at the initial point, the body has a certain amount of kinetic energy plus a certain amount of potential energy. Then at the final, after transformation, the kinetic energy is at final point plus the potential energy at final point. So the sum of the energy, total energy input, and the sum of energy, total energy output, stay the same. But the kinetic energy or the types of energy within this can be different. For example, KEI, kinetic energy at the initial point, can be different to kinetic energy at the final point. For example, this one we have 5, this one we have 1. Okay, we left with 1 joule. But the total energy at the input need to be equal, the same to the total energy at the output. Okay. Other types of potential energy function can be added to modify this equation. Okay, so if we have other types of energy, pressure from the pressure energy, energy from other heat source, work, heat, etc. So this is elastic potential energy. So if we want to calculate the potential energy stored within the spring when we compress or expand the spring, so we use this. Okay, potential energy 1/2 kx square. So k, you know, k is the Hooke's law. Hooke's law. So it's a constant value, and s is the total displacement of the spring. So this one in static, static. So work energy theorem. So in order to to calculate, to evaluate the total work produced within the spring. So we need to take into consideration the kinetic energy, the displacement, the potential energy due to the gravitational force, and the potential energy due to the elasticity. So then we can calculate the work produced from the spring. Transferring energy by work by applying a force produce a displacement of the system. So like just now, like the if we push or pull, like we push the book here, so we are applying the force to this body, and it will be displaced, produce a displacement. So that also is one types of transformation of work using a displacement force. And then heat also, like just now, cup of hot coffee, etc., etc. Mechanical wave, okay, this one, if you have sound, water, usually something nature, okay, means that the wave can, the sound wave, okay, or the radiation just now, the wave can be transformed through a medium. So we can produce also energy using this mode, okay, this type of form, mechanical wave. Electrical transmission due to electrical, okay, means we use electrical power to transfer the energy. So for example, like hair dryer here, from the electrical energy, the mechanical power, etc. So we transform the energy to heat, okay, to dry out our hair. So again, electromagnetic also generation, like also wave, any form of electromagnetic waves. Okay, so energy is conserved again. Energy and mass. Okay, so if we involve with electromagnetic waves, etc., we need to take into account the speed of sound or speed of light, which is, it is a constant value, 3 times 10 power of 8. Speed of sound. Ni kalau ada, if you have a wave, like electromagnetic wave just now. Okay, specific heat. Saya ada berapa slide lagi? Okay, tak banyak dah. Okay, specific heat. It is an intensive property as our unit. So the units is, usually we use this one, kilojoule per kilogram per Kelvin. Okay, a substance that will enable us to compare the energy storage capability of various substances. Okay, so it is a property, a parameter that we use to characterize how much the energy can be stored within a certain body, a certain solid or certain fluid. Okay, so if you want to understand, you just look at the units. Okay, means that it is a specific heat. So it is types of energy. It's like energy, just that energy per mass and per temperature, Kelvin. Okay, means that we try to characterize how much the heat or the energy is being transferred during within 1 kilogram of mass. So it is a rate, and per 1 Kelvin of difference of temperature. Okay, so or other definition to compare the energy storage capability. So capability of the body, the material. So each solid, fluid, gas, liquid, etc. has different specific heat. Okay, so the specific heat is a constant value. Okay, it's not actually constant, but for thermodynamic undergrad, we just take it as constant. Okay, so it is a constant volume, is fixed, but it depends on the body, the substance, whether it is whether it is a solid or which type of solid. Okay, different solid have different specific units, different liquid has different specific unit, different gas has different specific units. So it is a property of that substance. Okay, you don't need to remember, but the one that usually we will use, so after a certain time you will remember eventually, which is for air. Air, so specific heat of air is 1.005 kilojoule per kilogram per Kelvin. 1.005 or 1005 joule per kilogram per Kelvin for air. Another one for water, okay, I forgot. But that one, water and air is the one that we usually use. Okay, other than that, you don't need to remember. Okay, so define the energy required to raise the temperature of 1 kilogram of a substance of 1 degree centigrade. So that is the meaning. We define the energy required. Okay, so the capability of that substance to heat in order to raise the temperature of 1 kilogram of the substance, solid, liquid, etc. Okay, this is its definition, but from this definition that we produce this unit. Okay, so how are we going to relate the specific heat with the first law thermodynamics, conservation of energy just now, work, heat just now? Okay, we see the link. Apa kaitan dia dengan tadi ya? Okay, this energy or heat, the heat, okay, energy to heat, energy to work, okay, is dependent on the type of process executed. Okay, in energy thermodynamics we focus on two types of specific heat. So we have two types of specific heat, which is constant volume specific heat and constant pressure specific heat. Usually the one we use is constant pressure, but still you need to know constant volume. For basic thermodynamics, constant volume, constant pressure. But after this, for gas turbine, for propulsion, we usually only use constant pressure specific heat, CP. But you still need to know constant volume process. Okay, the boundary work is 0 and the specific heat is identified by subscript V. Okay, so for constant volume process, we assume that the boundary work is 0. Remember, if the boundary work is 0, means that we have constant volume. Okay, remember the question that I asked Ashwin just now. Okay, if we have constant volume, so the boundary work is 0. Okay, because the PdV just now. Okay, the work is done. So in order to characterize this specific heat, CV, constant volume, so imagine the boundary work is 0. Okay, so the specific heat is identified as CV, V subscript here. So from the first law of thermodynamics for closed system, closed volume, like for power plant, gas turbine power plant, piston engine. Okay, so we have the first law of thermodynamics. Delta Q means the change in the heat minus the change in the work equals to internal energy. U is internal energy. So this one is one type of first law of thermodynamics, conservation of energy. Okay, so during a certain process, there might be change due to heat, change due to work, and change to internal energy. Internal energy is usually the change in terms of temperature and pressure, internally within the fluid. Okay, so if constant volume boundary work 0, so this one slash out, so we have delta Q equals to du, means that the change in the heat is equal to the internal energy. But we also know the definition, delta Q is CV delta T. Definition from the definition. This one, definition delta Q. Okay, delta Q is CV delta T, means specific heat times the difference in the temperature. So we can also write CV delta Q over the difference of T. Okay, I don't know if you know secara matematiknya, there is a difference between if you write delta like this or if you write a triangle like this, which is means a variation, or if you write D like this, even though usually we understand that delta or this triangle variation and D is a difference between certain point to certain point, right? But mathematically, actually, it has different level of difference. Usually, if you write delta, means that the change of the D or the difference is very, very small. And then D, the derivation here. And then this triangle variation. So means that if you write this triangle, means that there is a difference, but there is a difference, but the difference is quite big. Otherwise, if you write delta, means that the difference is very, very small. Okay, so that's how mathematically it means. Okay, so CV du over dt. Just rewrite this one. Okay, so this is the definition of CV, specific heat for constant volume process. So we have du, we replace with CV dt here because due to this definition. So we have the internal energy, the change in the internal energy it depends on the change of the temperature and the specific heat. So means that if we know the change of the temperature, maintain temperature from initial point to final point, then we can calculate the amount of energy produced, the internal energy, which is equals to the heat transfer. Okay. So second one, constant pressure process. For constant pressure, again, the first law of thermodynamics, the same as just now, same as this one. So for this one, we cannot neglect the Q and W. So du plus PdV, so we just, the boundary work W, remember boundary work W, PdV, and just rewrite this one. Okay, so we have, okay, U plus PV is enthalpy. Okay, this one is mentioned in first chapter. Okay, U plus PV is enthalpy is energy also. So enthalpy is written as H. So after rearrange the equation, the term, etc., we have delta Q, the heat transfer for constant pressure process is equal to the enthalpy. So means that if you want to for constant pressure process, if you want to calculate the enthalpy, the total energy, we just focus on the delta Q, the heat transfer. Okay, so delta Q, specific heat for constant pressure, we have dH over dt. So the change in enthalpy with temperature at constant pressure. Very specific heat. So specific heat is a constant, a fixed volume, a fixed value for each substance material. So again, internal energy, enthalpy, and specific heat to summarize all these things. So for ideal gas, okay, for ideal gas, we have PVRT, the ideal gas equation. Remember PVRT, previous chapter. Okay, so using the definition H, enthalpy is U plus PV. So the same as this one, U plus PVH. So U plus PVH. So replace the PV with RT. We replace the PV with RT. So we have here, for ideal gas, we prove here that the enthalpy only depends on the temperature. Okay, because U, internal energy, is the energy due to the temperature. Okay, and this one, R is a constant volume, a constant value. Okay, R is fixed. So the one thing that changed is the temperature. So means that from this equation, we know that enthalpy for ideal gas depends on temperature. From the the specific heat relation, so this one du Cv dt. So if we integrate that one, we have U2, the internal energy equals to Cv dt. Okay. Okay, so this one, you want to describe the internal energy U, the equation for internal energy, and the equation for enthalpy H for ideal gas. So if you have ideal gas, you want to solve to calculate the internal energy or the enthalpy, you use this equation. Okay. Taking average value, okay, sama lah. Okay, so delta U is CV delta T, delta H for is CP delta T. So the difference is for internal energy, we use specific heat, constant volume. For enthalpy, we use specific heat, constant pressure. Okay, the equation is derived from here. So this is for ideal gas. Gas mainly. Apa lagi? So this one if you use other forms of R, okay. Okay, okay, other ideal gas property is what we call as specific heat ratio K, or sometimes we write it as gamma. Gamma macam ribbon tu. Okay, gamma or K is specific heat ratio, also a constant, a fixed value for each material or each substance. So for gas, for ideal gas, usually we take it the value 1.4. For air, usually we treat it as 1.33. Okay, 1 point something. So different fluid has different specific heat ratio. So it's a constant value. So specific ratio is actually the ratio between the specific heat at constant pressure over the specific heat at constant volume. So if we rewrite the equation, we have this. Okay, means that we can, if we have the value of R, the gas constant, and we have the value of K or gamma, the specific heat ratio, we can calculate directly the CV. We can find the CV and CP of that substance. Oh, Habida. Oh, so okay, I will show you the ideal gas. Means I didn't include the for solid and liquid. It's okay. So because we mainly will use example for ideal gas. Okay, now what time is it? For 15, for 16. Okay, so in the tutorial homework that I uploaded in Putra Blast, I show you just now. This one, tutorial 3, need to be done due date next week. So in here, I think, if I remember, I include exercise 2 and 4 here. So it's actually the exercise that we need to do in class, but I put it also in tutorial. Okay. I think we can do at least, I can explain at least one, exercise 1. The rest, I think we will do next week, insyaAllah, during our physical class, because actually it's quite difficult to explain all the equation online. Saya tak prefer sangat. Okay, tak apa. Okay, so look at the exercise 1 and then we finish. Okay, exercise 1, at least until 4:30. Okay, rigid tank contains air at 500 kilopascal and 150 degrees Celsius. Contains air at 500 kilopascal and 150 degrees Celsius. As a result of its transfer to the surrounding, temperature and pressure inside the tank drop to 65 degrees Celsius and 400 kilopascal respectively. Determine the boundary work done during this process. Okay, W. Okay, try to understand and try to think a bit before I show you the example. Okay. Okay, maybe kita boleh buat, we can do 1 and 2 because actually it's quite easy, not long. Okay. Okay, number 1. Determine the boundary work done during this process. Okay, if you read the questions, what can you derive? Okay, from these questions, what any idea how to do? I ask. Nahimuddin lah. Nahimuddin. Are you there?
Yes, betul.
Okay, exercise 1. Actually no need calculation. Okay, so you just explain what is the answer and why.
I think 0, right?
Why?
Because constant volume.
Okay. Thank you.
Okay.
Okay, correct. Okay, so actually no need calculation for exercise 1, but you need to explain, of course. Okay, so the things, the property change during the process, during the heat transfer, only temperature and pressure. Pressure from 500 to 400 mean it is expanded, and temperature decrease the heat transfer from 150 degree to 65 degree. But there is no within the tank, okay, the tank, the container, air, the air within the tank doesn't change during the process from initial to final point. So the boundary work, because we are talking about boundary work, so it means the boundary work means that the volume within the tank, within the boundary, the control volume doesn't change, the total volume from initial to final point. So so the boundary work is 0. Okay. Azan kejap. So you can try to read exercise 2 and think about exercise 2. Need some small calculation for exercise 2. Azan kejap. Okay. We look at exercise 2. So a piston cylinder device initially contains 0.4 meter cube of air at 100 kilopascal and 80 degrees Celsius. So we have volume, we have pressure, and we have temperature. The air is now compressed. Okay, so compressed, we decrease the volume within the air, compressed to 0.1 meter cube in such a way that the temperature inside the cylinder remains constant. So this time around, we have constant temperature. Constant temperature, okay? But the volume changed. So determine the work done during this process. Okay. So again, PDV. Okay, I'll try. Dah lama tak guna whiteboard ni. Sekejap. Mana? The whiteboard jam file kan. Okay. Okay. So soalan dia apa tadi? Okay, so we have volume 0.4. Sorry guna mouse je. Temperature 80 degree. And pressure 100 kilopascal. Okay, so again, here directly, even though it doesn't mention, we just assume that the gas is ideal gas. So ideal gas. So we can use the ideal gas equation of states. PV equals to RT. Here we use the PV, the big PV, not PV volume per mass, but we use the volume. So we need to use MRT because we have volume in terms of meter cube, not meter cube per second. So PV equals to MRT, ideal gas. Okay, so R usually is a constant. Mass also doesn't change. Here, doesn't make any change in terms of mass. The total mass is the same. Just that pressure, volume, and temperature also the same. Constant temperature here. So MRT doesn't change for this process. So we can just call it as a constant or C, whatever the term that you want to write. So this part is constant. So from the boundary work, the definition of boundary work, P integration of P dV. So we need to define what is P. Okay. So this P, in order to define the P, the pressure, we need to understand how the process, the path taken for the process. So for here, P is constant, MRT. If you want to write MRT also can. Okay, over V. So constant over V, again dV. Okay, we just change P. Understand? Because ideal gas, MRT, mass the same, R gas constant, temperature for this process is constant, 80 degrees Celsius throughout from initial to final state. So we just, constant, we can take out the constant, normal integration. So we have left with over V. Okay? So mathematically, integration of 1 over V or 1 over X is ln V, ln X. Kan? Ini matematik So ln, so constant. Again, so integration ln V2 over V1 lah. Okay, 1, 2. Okay, so given here V1, V2 0.4 and V2 0.1 jadi V1, V2 0.1 meter cube. Okay, so just include here V1, V2 ln. Okay, so V2 first V2 dulu final lah. So 0.1 over 4 or 1 over 4, so 0.25 a quarter. So times and then ln, and then times MRT don't forget, times the mass. Okay, the mass can be slash out, okay, because M1 and M2 remain the same. So we just have PV equals to RT. Ni, macam ni. So P2 so this one mass constant, R of course constant, T also constant. So this one can be slash out. Okay, so you just put in the value, all the values here. So you calculate, you get boundary work is negative 55.5 kilojoule. Okay, usually we leave it in kilojoule because this one kilopascal. Okay. So the negative sign here reflects, okay, that negative work. So reflect that the air, the fluid is being compressed. Negative work just now, right? Negative work means we lowering the piston. Okay, lowering the piston, so air is compressed. So negative. So betul lah, correct lah. Okay. Okay, just to verify whether we got the correct answers. So we can see here because the volume is being reduced from 0.4 to 0.1, so the volume reduced, so obviously you will get negative here. Okay. So that is exercise 2 just now. So this exercise 2 is included in your tutorial homework. Okay, in Putra Blast, so you can do it. We already have the answer. You have the answer. You can do it directly after this. And then you can look at exercise 3, exercise 4. I have also exercise 5. Okay, so exercise 3 and 5 is just for your practice, but exercise 2 and 4 is in the tutorial homework assessment in Putra Blast. So need to answer that properly, yeah. Okay, otherwise if you have time next week, inshallah, during our class, Wednesday afternoon, we will try to do the 3, 5, etc. Hopefully. Okay, I think I will finish here. Okay, I'll finish here. So we finish earlier. Okay, any questions from you guys? Oh, test 1, week 6. Weeks, I agree with Izani just now. You will do in week 6 together with the group. So week 6, 15, betul? 15 November, if I'm not mistaken. 15 November. So we use the time right now, 3 to 5 or 3 to 4:30. Not sure yet whether 1 hour and a half or 2 hours. After that, we can continue our class. Okay. Okay, any more questions? Okay. For attendance, since we are doing online, so I need to give you a Google form. Can you open the Google form and fill in the attendance? Just your name and your matric number. Using your UPM account. Okay, I see already one response. Okay, so we finish here. After you fill in the attendance, you may leave. Okay, so I'll see you guys next week, inshallah, next Wednesday afternoon. Thank you very much. Assalamualaikum.
Medium.
Yeah,
Apa jawapan tadi?
negative 55, negative 555.
Negative 555.
Negative 55, negative 55.
Okay. That unit eh? What?
Work mana what?
Joule.
Work energy lah, kilojoule.
Kilojoule. Okay, baik.
Okay.
Terima kasih.
Doktor, tadi bila tarikh test 1 tu?
Week 6, 15 November kan? Kira je lah minggu ke-6.
Okay, baik doktor. Thank you.
Thank you.
Okay, fill in the attendance 70 response already. We have, tak tahu tadi berapa, 22 I think of you. Okay, bye. Stop recording.
Thank you, doctor.